Okay, so this question is different. We're still going to do a precipitate forming. We're still going to do that. We're going to do the comparing to Q, like to KSP. However, this is more like really what would happen in a lab. You have two solutions with different volumes or the same volume, it doesn't matter, and you mix them together. So this is really double displacement. We have calcium chloride and sodium sulfate mixed together. We're going to mix calcium sulfate and sodium chloride. So similar to what we've been dealing with, we don't care about the spectator ions because they come to the event, they don't participate. So writing out the double displacement reaction, you actually don't even really need to do here because you're going to be given a KSP. And the KSP value is for calcium sulfate. So that is the substance that we're concerned about. I apologize, I just realized this says 3.6 times and then the 10 to negative 5 is over here. I don't know if it's like that in your note. I'm just going to fix it here quick. If I can, no. There we go. So we are going to focus on the solid. And what's the solid? Calcium sulfate, because that's the KSP value we're given. Okay? So we only care about the solid, which is calcium sulfate. So that is the dissociation equation that we're really concerned about. I think if you printed the notes off, you can fill it in like in the boxes. It's pretty good, this one. So we have calcium and we have sulfate. Again, we're kind of streamlining, I won't say cheating, but kind of streamlining stoichiometry. So when you have a solution that's got calcium in it, so the calcium chloride, and then you have a solution that's got sodium in it, the sulfate in it, the sodium sulfate, then logically you can't destroy matter, right? So whatever concentration it was initially from the other solutions, that's going to be what initially we have in our flask or vessel. So those numbers, they're given in the question. It says 0.1 molar calcium chloride and 0.04 molar sodium sulfate. Okay, so what happens is you have these two solutions. They're 100 milliliters each. That's what it says in the question. And then you mix them together. So when you have a solution and you mix a solution together, two solutions together, what happens is you're going to increase the volume. So you have to remember that aqueous solutions mean dissolved in water. So if you add more water to a solution, it's not going to maintain the same concentration. It's going to get weaker, or what we call dilution. So in grade 11, when you diluted a solution, you had to use this formula, the dilution formula. Okay? So you can write it as C1V1 equals C2V2, or like 1 is initial and 2 is final. What is the new concentration going to be after we increase the volume by adding more water? So logically, it's going to be less. So once we add our two solutions together, the calcium concentration is going to decrease from 0.1 and the sulfate concentration is going to decrease because there is more water. So we're really, this extra part here, this extra calculation before we can calculate Q has really nothing to do with grade 12. It's just the principles of chemistry. If you add more water to something, it's going to become less concentrated or diluted. What is that new concentration going to be? We can calculate it, okay? So the volumes here happen to be the same. They don't have to have the same volume. They don't have the same concentration. Whatever values you're given, just plug them in, okay? So the total new volume is going to be 200. We're going to add the two solutions together. Initially, these are the concentrations, and the volume for each of them is 100, happens to be the same. We're going to solve for the new concentration once we've changed the volume. And it should be less. It should be diluted. You're adding more water, less concentrated. And since we have two ions that have different concentrations and then we're going to have to do this concentration calculation, dilution calculation twice. Okay, so we have for calcium, its initial concentration was 0.1 and we had 100 milliliters. If we change the volume to 200, what's the new concentration going to be? So 0.1 times 0.1 divided by 0.2 is 0.05. Usually in grade 11, I make you change the milliliters to liters when you do this calculation. But really, because the volume's on each side of the equation, you're kind of multiplying by 1,000 and dividing it as well. So you can actually leave this one as milliliters. Just don't tell kids in grade 11. But I didn't hear. I changed it into liters like we did last year. And then you have to do a similar calculation for sodium. Because sulfate, sorry. Sulfate is 0.04, it's not 0.1. It's got a different concentration initially. But in both cases, their concentration went down. So it went from 0.1 to 0.05, 0.04 to 0.02. Yes, that's perfectly half because we doubled the volume perfectly. So that makes sense. Double the volume makes the volume of water makes the concentration half as strong. So now we are ready to do Q. Now we have a calcium concentration and a sulfate concentration in our new solution, and we are going to figure out how does it compare to the given KSP value to see whether a precipitate forms. So this value here, this 3.6 times 10 to the negative 5, it is given, has to be given. Okay, so again, this is where things get annoying because this is scientific notation, and you might think that this number is smaller than this one because it's 1 and 3.6. But really, this is -3. So that means you go 3 decimal places, 1, 2, 3, like 0.001. And this one, you go 5. 1, 2, 3, 4, 5. So this is actually smaller. So now our Q is too big, which means it needs to get smaller. So you have to increase the bottom of the fraction, which is a shift left. More precipitate. Or you could say solubility decreases. That's the same thing. Less is dissolving, more solid is forming. Okay. So for Okay, so for the common ion effect, this is an application of Le Chatelier's principle, basically. And again, the reason that we have to consider things like this is because you can decrease how much will dissolve, or you can increase the formation of a precipitate if you add a substance that has a common ion. So something that whatever you add, the solution you add would be 100% soluble, and you're like, oh, who cares, whatever. It doesn't make a precipitate, but then it can influence the formation of precipitate in a different substance. So you have to be careful, and it's just an application of Le Chatelier's principle. So if you have whatever your solid is, and then the ions are on the right hand side, since ions are always on the right hand side, you're just increasing the product, and you would know if you increase the product, it has to use it up, so it shifts towards the reactants. What's in the reactants? The solid. Mhm. Okay. So we've so far been dealing with the solubility of a substance in water. So water has no ions if it's pure water, which it should be. So then we're going to qualitatively predict. So what happens if you add a solution of sodium chromate? So lead chromate, the chromate ions are on the product side. The substance you're adding will always be 100% soluble. So now you're increasing the concentration of the ions. So this is the solids um, dissociation equation. Again, how can you be sure? You always want to look for KSP. KSP for lead chromate is, so lead chromate is the one that's the solid, in case you're not sure. And we're going to add sodium chromate. So really there are plenty of practical applications to this. So let's say you have a solution, and whatever you're going to do with the solution, who knows, but it's going to be used some way by humans. Is lead good, or any mammal, is lead good for us? No. So this is actually called selective precipitation. Can you see ions with your naked eye? Are they easy to extract? No. Can you see a solid? Yes. So if you have lead ions in something, that's very bad. It affects our brains, right? It's not good for us. So you can add a solution. Now sodium, okay, so sodium isn't great for us either, right? We have to watch our sodium levels when you get to a certain age, but it's certainly not going to make you crazy like lead will, okay? Irreversible changes. So you can add a solution that's pretty innocuous and then get it to form lead chromate. And then the lead chromate can be extracted from the solution. So you have less lead. In this case as well, chromate, it's not great for you. Also the chromate, and you can get it out of the solution. And it's called selective precipitation. So yes, I mean, in a lab, whatever, you want to do the calculations, but in a real world way, if you choose a job where maybe you're in charge of looking at the effluent water released by a factory or something like that, really has nothing to do with chemistry, that could be part of your job, trying to increase the cleanliness of the water and stuff like that. So especially moving forward, I think that water is going to become more of a crisis. Then maybe you will have to do stuff like this. Oh, sorry. And then if you're shifting to the left, because always ions are on the left, more solid is produced, solubility decreases. So less is dissolving, which is good. We don't want stuff dissolved in the water that we don't want in there. We want it out, especially lead and chromate. Okay. So that's the qualitative side to it, and you can prove this quantitatively. So in this case, you're given the amount in water, 4.8 times 10 to the negative 7. What we're going to do is we're going to solve for the new solubility in a solution that has a common ion. So the compound with the common ion is going to be 100% soluble. So you don't have to worry about trying to check whether sodium chromate is a solid. It has to be, or, there's no point to this really. And it's going to be 1-to-1. Similar with that dilution question, if you were going to do this normally, it would be 1-to-1. Can you have to do stoichiometry? Yes. That just adds a little bit to the math, which would be more, maybe not even in first year, to be honest, like upper years, if you're going to take chemistry. Just going to try something. Okay, so we do the same thing. ICE, cross out the solid. But the problem is now, so in sodium and chromate, the sodium, the metal, is not common, so it's 0. But this one now has a concentration. And this is going to influence the math, unfortunately. So still 0, so we still want plus x. Okay, so the KSP value way back up here is 2.3 times 10 to the negative 13. Yes. So when we do this, if we put 0.1 plus x, we're going to have to distribute, and we're going to get an x squared term and an x term, which means we would have to do the quadratic formula, which is fine. However, is this a very big number? No, it's like tiny, right? 12 zeros and then 2, 3. So when we solve for x, and let's say you go over here and type in 0.1 plus our x value, your calculator is literally going to say 0.1. The x value is so small that it is not going to change this value. So we can do something called a 100 rule approximation. And the reason I didn't cut out this entirely, I didn't stop doing this, we're actually going to use the 100 rule in acid-base equilibrium as well. And I was helping someone with chemistry in university, and I was like, I don't think you should use the 100 rule approximation, and they did. So I was like, okay. Really, you're supposed to look for 2 decimal places. That's what 100 is. So you need 2 decimal place difference between negative 13, and this can be rewritten like this, negative 1. So is that 2 decimal places? It sure is. You can divide them. If you divided them, you would get 4.3 times 10 to the negative 11. So basically, we just want the concentration to be 100 times bigger than the KSP, or 2 decimal places. So the easiest way to figure it out, if you don't like decimal places, is just divide them. .3 times 10 to the power of 11. That is insanely bigger than 100. And sometimes students are like, Ms. Todd, I hate the 100 rule. It's really meant to help you. So the term that has a number plus x, we are going to ignore the x. So you say approximately equal to 0.1. So then in our equation, we don't need to include the x. Here, 100 rule is 0.1, 100 times larger than 2.3 times 10 to the negative 13, question mark. So then I just divided them, 0.1 divided by 2.3 times 10 to the negative 13 equals 4.3 times 10 to the power of 11. Okay, so we are ignoring the x here. You can't ignore this x, we need an x. But whatever is with the number, we're going to use this approximation every single time, even in the next unit when we do this, okay? So now you divide by 0.1. You can use the quadratic formula, but you don't need to. You can prove me right. You can do 0.1 plus 2.3 times 10 to the negative 12 in your calculator, and it's going to say 0.1. It is such a tiny number, it is not going to influence that 0.1 at all. So then let's make our lives easier, right? So now this number is so much smaller than the solubility given in the question, 4.8 times 10 to negative 7. This is tiny compared to that, right? So the decrease in how many ions are in the solution is pretty great, which is good. If you don't want lead and chromate ions in your solution, it would take them out, so then you can extract the solid. No more lead and chromate in your water. So no common ion effect, no math. Maybe, I can't remember if there's like a Le Chatelier's principle question, but it would just be like, if you increase the concentration of this, it shifts left. You know, like that, maybe that, I can't remember. No math for this, and no dilution. You'll just be given concentrations, and you have to calculate Q and compare it to KSP. But not on tomorrow, on the exam. So you can do the review if you'd rather look at last year's assignment. No multiple choice. There is a little bit to write about Le Chatelier, I guess, like how do you increase the yield? If you shift left, why do you shift left, or whatever. But no graph, and then basically like one kind of problem, one kind of math problem each. So you can look at last year's assignment on D2L. I'm almost done the solutions. If you want to practice that, you could do the review, you could do the worksheets. It's up to you. But this solubility stuff from today is not on tomorrow, only on the exam, the part 2 exam, the one on November 11th. In topic number 2 on the worksheet, number 3 is pretty tricky. It's not going to be that tricky on the exam either.